So in this lecture, let us discuss multiplexers. So a multiplexer is a combinational circuit and multiplexer means many inputs to one output. That means it has many input lines. Those input lines contain binary information. So in the input side you have many input binary information, and in the output you have only one output line. Okay, only one. So how do you select one to the output? Somehow you need to give the connection between many inputs to one output. So there is something called some control signals. That control signals are called selection lines. So you have to select among the inputs. Okay, so I have three types of arrow mark in this block multiplexers. So input, the left hand side input, in the right hand side I have output. So I need to choose. Okay, so somehow I need to select. So that selection can be done with the help of selection inputs. So selection inputs basically select any one input to the output. Okay, so the selection of a particular input line is controlled by this set of selection lines. And normally in the input side we will be having 2 power n input lines, and here we will be having n selection lines. So if you put different combinations, for example, if you take 2 bits at a time, if I 0 0 0 1 1 0 1 1, these are the combination of my selection lines. If 0 0 is there, then first let me call there are 4 inputs. So 2 power 2, that is 4 inputs. So in the multiplexer I have 4 inputs, 2 selection lines, as I said 2 power n inputs, n selection lines, and 1 output. So this is my multiplexer. Generally the multiplexer in short form it is called MUX, MUX, MUX. Okay, so the inputs are, let me call I0, input 1, input 2, and input 3 and 4. So there are 4 inputs. So based on the selection input combination, if 0 0 is applied, then I0 is connected to the output. If 0 1 is applied to the selection lines, then I1 is connected to the output. If you give 1 0 to the selection input, then I2 is connected to the output. 1 1, then input I3 is connected to the output. So that's what your multiplexer is basically doing. So it is also called a data selector. You have many inputs and you need to connect only one person. So such type of operation is done by multiplexer. It has huge number of applications in digital system. It's a very important circuit. Okay, so generally if you have n selection lines, I have 4 combinations, right? So that's why I have taken 4 inputs. It's not necessarily that you should be having 4 inputs. You may have less number of inputs also. Now let us take a 2 to 1 line multiplexer. So in order to explain the concept, so insert pictures. Okay, done. Yeah, so this is my logic diagram of logic diagram of 2 inputs. See, I have 2 inputs, I0 and I1. So 2 to 1 line multiplexer. Okay, Now I have two inputs here, I0 and I1, and this S stands for selection inputs. Okay, don't forget the general concept. I have n number of selection lines, 2 power n number of input lines. So here the input lines 2 to the power 1, and here selection line is 1. So only one selection line and two inputs. Okay, so this logic diagram or this combination circuit has two input lines. So this is called data lines. So two input data lines and one output line and one selection line. Now let us assume that when S equal to 0, what is going to happen? So you are applying S0 here, and 0 comes here, and here I1 times 0, this is 0. So here also 0 comes. Now this 0 appears here as 1, and this 1 comes here, and here the input is I0 times 1, it is I0, and here also I0, so the output is I0. So when the selection input is 0, the output Y0 will be, output Y will be I0. Okay, so when S equal to 0, the upper AND gate is enabled. Therefore this I0 has a path to the output. Now let's take the next combination when S equal to 1. When S equal to 1, what is going to happen? When S equal to 1, then this 1 comes here, and here this is I1. So output of these two input becomes I1. So here also I1, and this 1 becomes 0 here, output of a NOT gate. So this is 0 and this is I0. So this is I0. I'm sorry. So this is 0. So my output is I1. Therefore Y equal to I1. That's it. Okay, so when S equal to 1, what is happening? The lower AND gate is enabled. Therefore this I1 has a path to the output. So therefore this multiplexer acts like an electronic switch. So based on the selection line input, it switches between the two inputs. Okay, so it selects one of the two sources, two sources. Now sometimes this multiplexer logic diagram can be represented in terms of like block diagram. So let me bring that diagram also. Okay. Now if you look at this multiplexer diagram, this is a typical way of drawing the diagram. It's not like a rectangular box or a square box. It's like a wedge shaped symbol. So this is typically people will use to represent the multiplexer. Okay, so sometimes we represent the multiplexer using this type of symbol. Okay, so one side the length is little long, little larger, like this. It's like a wedge shaped symbol. And by looking this diagram, you can understand that the data is going from the left hand side to the right hand side. It looks like an arrow marker, that's it, nothing else. Okay, so it suggests us visually how a selected one of multiple data sources is directed into a single destination. It indicates the flow. Okay, so how the flow is happening here. So it goes from input side to the output. And sometimes, as I said, the multiplexer is often labeled MUX, MUX in the block diagrams. Okay, so that's how you represent the multiplexer. So you have the selection lines, selection input line, and this is data input line, and this is my output line. So two inputs and two types of inputs and one output in a multiplexer. It is slightly different from your decoder and encoders. Okay, decoders you have input and output, but here we have two types of inputs. Okay, one type of input is to select the other inputs. Now let us take a little slightly more number of input multiplexers. Pictures. I have taken the screenshot from the textbook Maurice Monod. So this figure you can get it in the Maurice Monod also. Now look at here. This is the logic diagram of you have 4 inputs. Draw. You have 4 inputs, 4, 2. Okay. See, I have I0, I1, I2, I3. So 4 number of inputs. So 4 to 1 line multiplexer. This is similarly you can construct a 8 to 1 line multiplexer, 16 to 1 line multiplexer, like that. But the number of inputs should be in terms of 2 power n, 2 raised to the power n. So I can have 2 to the power 1, 2 inputs, 2 to the power 2, 4 inputs, 2 to the power 3, 8 inputs, 2 to the power 4, 16 inputs, and so on and so forth. Now each of the 4 inputs I0, I1, I2, I3 is applied to one input of AND gate. So let me call this AND gate 1, 2, or let me call A0, A1, A2, A3. There are 4 AND gates. Okay, I0 is connected to A0, I1 is given to the input of the second AND gate, I2 is given to the input of third AND gate, I3 is given to the input of fourth AND gate. Now if you look at these things, it looks like a decoder. If you remove this I0, I1, I2, I3 lines and look at the circuit diagram, then it looks like a decoder, right? So and remove this OR gate also, then looks like a decoder. And here I have selection lines S1 and S2. Okay, so if you remove this OR gate and the input lines, then it's a decoder. So I have 4 inputs and 4 outputs and 2 inputs. Now this output of the AND gates are applied to a single OR gate. That provides the one line output. So you just take 4 input OR gate and this nothing but a single output. Now let us write down the function table for this. So so it's very simple to explain actually. Let me delete all this. Now I have the selection lines S0, S1. Okay, now I take 0, 0. Here this is 0 and this is 0. So this 0 comes here as a 0 and here it becomes 1. So this 1 is coming here all the way to 1. Okay, so this input is 1 and this 0 comes here and it becomes 1. So this 1 comes all the way to 1. So both the inputs are 1 and this is I0, therefore this one is I0. Now this 0 is coming here. If any one input is 0, the output is 0. And this 0 is coming over here. If any one input is 0, output is 0. And this 0 is coming over here and this is 0, output is 0. So only one input is directed to the input of your OR gate. Rest of the remaining 3 inputs of your OR gate is 0 at a time. For a given any combination, only one input will be high. That doesn't know, okay, only one one input comes to the input of OR gate. Similarly, you can take the other combination. Therefore, this is 0, this is 0, this all three inputs are 0 except the fourth input I naught. So therefore, y is equal to I naught. So output is I naught. So this is my first entry in the truth table. Similarly, you can apply the rest of the combinations also. Now you take a 0 1. Now S1 is 0 and S2 is S0 is 1. So this 1 comes here, it comes all the way here, it is 1, and the 0 is 0, here it 1, and this 1 comes here, both the inputs are 1, and the third input is I1 to this NAND gate, second AND gate. So this is I1. Now this 0 comes and here it becomes 0, so the output is 0. Okay, and here the 0 appears here, so therefore output is 0. If any one input is 0 of an AND gate, then output is 0. And yeah, this 1 comes here and this is 0, so it comes all the way to 0, therefore output is 0. So only one input is active, that is I1, rest of the three inputs are 0, therefore output is I1. So this is I1. Similarly, you can work out for rest of the two combinations. If I give 1 0, then I2 will be selected, 1 1, I3 will be selected. That's it. That's how the multiplexer works. So the outputs of the AND gates are applied to the input of the OR gate. Okay, so the output of OR gate provides only one output. Okay, this is my function table, or I can call truth table, or whatever it is. Okay, now as I said, when you apply 0 0, then I naught will be selected. For 0 1, I1 will be selected, 1 0, I2, 1 1, I3. Now look at the subscript. Okay, the subscript is 3, and 3 is equivalent binary. The equivalent binary representation of 3 is 1 1. And look at I2, the 2, you take the 2, this 2 is the, if you take binary representation of 2, 1 0. Here this 1 1, if you represent 0 1, and 0 0 0, that's it. So in that way you can remember this. Therefore, for a given selection input combination, the circuit provides a path between the any one input to the output. Okay, so it provides a path from the selected input, either S0, so either I0 or I1 or I2 or I3 to the output. So that is why, for this reason, it selects any one input now. So this is called data selector. And it provides a path from any one input provides a path for any one input. Now as I said, if you remove these input lines if you remove the input lines and the OR gate, then the circuit is nothing but a decoder. Okay, so and that's it. That's all about the multiplexers. So if you remove this line, this line, this line, and this line, and then the OR gate, then you'll get basically a decoder. Okay, so then you'll get a n input to 2 power n output lines. Okay, this is one output, this is one output, and this is another output, and this is another output. So you'll get a n by 2 power n decoder. See here 2 and here I have 4. So n2 2 to the power n decoder you'll get. So basically a multiplexer is constructed with the help of n2 2 to the n decoder with the 2 power n inputs and 2 power n input OR gate. So multiplexer is nothing but n2 2 to the power n decoder plus 2 power n input data lines plus 2 power n input OR gate. I told you already, okay, so if 2 power n input OR gate is not available, then you can go with a multi-level implementation. That's it. Okay, so therefore in general a 2 power n2 1 mux is constructed by this way. Okay, from a n2 2 power n decoder by adding 2 power n input data lines and okay, this 2 power n data lines will go, each line will go to one input of the AND gate. Okay, there are 4 AND gates, so I have 4 inputs. Okay, the output of these AND gates are applied to a single OR gate. Okay, so that's how you can construct the multiplexer. Now the size of the multiplexer is specified from the number like 2 power n data input lines and a single output. So don't forget this, it always give only one output line and it selects among the inputs. And to do this operation from 2 power n data input lines to single output line, I need to control the circuit. Somehow I need to do the selection. So that is done by with the help of selection lines. Okay, like as in decoders we have something called enable lines. Similarly in the multiplexer also we have another input something called enable lines. Okay, so the enable lines will enable any one particular multiplexer. For example, here I have 4 to 1 mux. Similarly, let me take another 4 to 1 mux. Then with this help of these two, I can construct 8 to 1 mux. So in such a case, I need to have another input, some extra input, that is called enable lines. If you have the enable lines, at a time either this multiplexer will be enabled or this multiplexer will be enabled. So that's the purpose of what you call enable lines. If you don't have enable, then it's very difficult to scale the multiplexer circuit. Okay, so typically you may not have like 64 inputs to one output multiplexer. What you do, 8 input to one output max. So like that, what you take, 8 number of 8 input multiplexers. First you combine 8 plus 8 will become 16, and again take another 8 plus 8, again it becomes 16. Then again 8 plus 8, again it becomes 16. 8 inputs, it's 16. Again add these two guys, 32 and 32 and then 64. Like that you can implement multiplexers. So in that case, this way also you can implement, or you can put all this 3, 4, 5, 6, 7, 8, this all are put together and you can get one output. So therefore with the help of lower input multiplexers, you can construct higher number of input multiplexers. Similarly, you can construct 128 to 1 mux also. So in such a case, if you don't have enable input, then it's very difficult to control the multiplexer. So for that purpose only, we will be having an enable input. So let us take one figure and understand this. There are so many disturbances today. I'm helpless. Okay, let me stop here and I'll continue this. Okay, so in the next lecture. Thank you very much, because so much surrounding noise.